Okay, there's one more interesting kind of electromagnetic plasma wave, and it shows you the connection between electrostatic and electromagnetic waves. Epsilon is this, which means that the phase velocity is 1 over epsilon is given by this. Now, if omega is very close to the plasma frequency, then the difference is very small delta. Um, that means that this has to be a number that's much smaller than
Much bigger.
um, you can get a solution if this, yeah, I guess if this is much bigger than 1,
Yeah.
and so if delta is equal to omega pe squared times omega pe squared over k squared c squared, then does that solve this? Uh, no, no, it's the other way around. If I choose omega very close to omega pe, but slightly above it, then I get what seems to be a very a wave with a very high phase velocity.
Okay. So,
Uh, but but here's the thing: it's oscillating at almost the plasma frequency, but just slightly above it. So in the limit of 0k, it's in electrostatic mode, oscillating at the plasma frequency, and it's a longitudinal wave.
mhm.
Uh, uh, uh,
Yeah.
and there's no electric field other than in the longitudinal direction. But if I made it a transverse field, it would be an electromagnetic wave, which is propagating its group velocity is very small. But its phase velocity is apparently very big because the index of refraction is so small. Uh, uh, we haven't talked about group velocity yet, but let's just say the phase velocity is allowed to be greater than the speed of light. The group velocity, not not. Uh, but what you have here is something that think about it. It's unlimited in phase. Suppose you had suppose you had a longitudinal plasma wave, but a plane wave. So it's the longitudinal direction is say the z direction, but in the x-y direction it goes on forever. It's the same and in
Mhm.
phase. Well, if you thought of it as being is propagating in the y direction, it has an infinite phase velocity because the wavelength in the y direction is infinite.
How could that be? That it's infinite.
Okay, imagine you have a box that's finite in the x direction and infinite in the xy direction.
Okay.
But think of the z direction as being a waveguide, and think of the direction of propagation as being in the x direction, in the infinite direction.
Okay.
The z dimension is finite, but that's just because it's a waveguide. But in the x direction, it's infinite. The wavelength is infinite because nothing
Okay,
depends
okay.
on x. Now, if you have a finite frequency and an infinite wavelength, then you have an infinite phase velocity.
Right.
So it's just, you can visualize the connection between an electromagnetic wave where epsilon is slightly above zero to an electrostatic wave where epsilon is exactly zero. One is the limiting case of the other. And another way to say this is that when you have a plasma, the photon has a mass, meaning a minimum frequency. That's what a mass is in quantum mechanics. It's the minimum energy something can have even when k is zero, even when the momentum is zero, because E squared equals k squared plus m squared. K is zero, E is equal to m. So with plasmas, you have omega squared equals c squared k squared plus omega pe squared. Is that correct? I think that's correct. It's the c. I think it follows from this. Let me just make sure. I mean, it makes sense. Omega squared has to be at least omega pe squared, and if k is small as an electromagnetic wave propagating in the electromagnetic direction, so to speak, so that the electric field is perpendicular to k, then in the limit that k goes to zero, omega squared is equal to omega pe squared. Otherwise, let's see what happens if I divide by c squared k squared. I want to make sure this is right. It's equal to omega pe squared over k squared times 1. Now, does that give this? Well, does it? It does?
This one gives this one.
This and this are the same?
Let's see, you can take it over to the other side. You have omega square minus omega 3e square over c square k square.
Actually, I should do it the other way. I should,
Yes, you're right.
what?
Sure, I had it. Absolut.
Yeah.
It's okay.
I guess so. I guess so. But I'm not seeing it. Anyway, I hope it's right. But the point is that this is just c squared k squared plus m squared in quantum mechanics. Right? I might have to put an h squared somewhere in here. Well, this is with h and c equal 1. Anyway, so the plasma frequency is just essentially gives the photon a mass.
Yeah, you get the same thing. You just have to multiply again by omega square, which is omega p square, and then you get the same thing. If you take this over here, divide by the what's it called? I forgot. And multiply by omega square both of them. And still
I multiply by omega squared.
and say in one side that omega square is omega p square.
What's the approximate omega square? If you write
If omega squared is approximately omega p squared, then it's the same.
Yeah.
I think you should use approximate sign instead of equal to, because you wrote the second line there in your right hand side, the right column.
Yeah.
You wrote omega square is approximately omega p square plus delta.
Yeah.
And then you estimate what delta would be if you assume that. So the next line is telling you what delta is.
No, but I know.
So then
But
you
I'm just asking if this is equivalent to this.
It is. So then you estimate then you know delta, then you plug in back into the equation.
Okay. I mean, if I had 5 minutes, I could do it. But
It's like going back and loop.
okay. So anyway, the idea is that you can have a very low something very close to the plasma frequency that propagates as an electromagnetic wave, and it's analogous to a particle propagating non-relativistically. And as far as I can tell, it's equivalent to saying that the photon gets a mass because it's in the presence of a plasma. And it's very similar to what particle physicists say when they say a gauge boson gets a mass because the Higgs field breaks its symmetry. What they mean is that the vacuum becomes full of Higgs condensates which act like a plasma, and they give gauge particles masses. I think it's very similar anyway. In fact, I think it's the same thing exactly, but I have a stomach aching. Now, this was without a magnetic field. When you have a magnetic field, you have to distinguish between the O mode and the X mode. The O mode is called the ordinary mode because the magnetic field doesn't affect it. The particle motion is along the field, so V cross B is 0. And for the O mode, epsilon is still this. Doesn't involve the magnetic field. For the extraordinary mode, again, K is perpendicular to B now. For circularly polarized modes, K was parallel to B. But now we're talking K perpendicular to B. So it's same situation, different direction for the K vector. The extraordinary wave is not purely electromagnetic because...
What do I mean by that?
Well, what does purely electromagnetic mean?
It's electromagnetic wave.
No, electromagnetic means that E is perpendicular to K.
Right. That's what happens in ordinary electromagnetic wave, no?
Yes.
So.
Not in the medium. the direction of the wave, not to each other.
That's what
As I remember.
he said.
E and B of the wave, but here I'm talking about B naught. K is
What is B naught?
B naught is the background field,
Ah.
constant field.
Ah.
So suppose E is perpendicular to B. The particles then, charged particles then get accelerated perpendicular to B naught. But then B naught exerts a V cross B force on them, right?
Mm-hmm.
And what direction is the V cross B force? It's V cross B0. It has to be perpendicular to both V and B0. But that's the K direction. Because E, we started out by assuming he's perpendicular to K, and B naught is also perpendicular to K, and E is perpendicular to B naught. So so V, which is originally in the direction of E, because that's the acceleration of charge, it starts moving perpendicular to B, but then the V cross B force makes it move parallel to K, and that causes charge separation in the K direction, which means that the particles are moving not only perpendicular to K but also along K, because they're going to start gyrating around B naught. So, I can draw a picture if you want. If B naught is like this and K is like that, and V starts off like that, or E, then eventually there's going to be particle motion in the K direction, and charged particles will move in opposite directions if they have opposite signs. So that'll establish a response electric field in the K direction. So that means that the wave is partly electrostatic and partly electromagnetic. And then you just have to, when you solve for the normal modes, you have to put in the whole dielectric tensor with x, y, and z dimensions and make sure that you got all the off-diagonal elements correct, and then you can calculate the normal modes. And Chen is for anybody who's interested, Chen is a textbook, and it's a good undergraduate class. It's a good master's level plasma physics textbook. It gives a nice, straightforward treatment of all these things.
Okay. You want to stop there?
Let me take a break for a few minutes.